Okay, so let's go ahead and get started. So something kind of interesting happened to me yesterday. So I went to get my teeth cleaned, and I was talking with the dental hygienist, and she asked me, what is it that you do? And I said, I'm a physics professor at UC, and her immediate reaction was, ew. So that was kind of funny, I guess. So today we're going to be continuing on with the electric potential, and we're going to, really what we're trying to build up to when we're talking about the electric potential is to talk about circuits. And so when we talk about the electric potential in the context of point charges, or we've actually already been talking about circuit elements already when we were talking about the parallel plates, because that's what's called the capacitor, it's a circuit element. But when we're talking about the electric potential in the context of charges, we can say, okay, well, this positive charge has some equipotential. I didn't draw this centered, so it should be centered on the charge. It has some equipotential contour because we know that we can write the electric potential as some function of R, and this is just going to be V as a function of R is Q over R. So all radii that are the same have the same electric potential. But what we can do is we can talk about differences in electric potential. So I have two arcs like this, so call this some V1 and call this some V2. And we can talk about the difference between these. The difference between these 2 points is what we call the voltage. And voltage is something that you've probably heard of before, because you need like a 9-volt battery for a smoke detector, and you hear a lot about it in the context of electricity, but that's really kind of where we're going in building this up, starting from charges and electric potential, and eventually we're going to begin today talking about circuit analysis. So let's look at the first question that we have, and this is really kind of to put all of the things together that we've talked about so far. And so this looks a little daunting at first, but this is just the table that I've laid out, only I've left a bunch of things blank. And so here what I do is I tell you that we have these two parallel plates. We have this electric field that points to the right. It has this electric field given by E vector is equal to the magnitude of E times x hat. That just says that we have some constant electric field that points to the right. And what we want to do is we want to fill in the rest of the table here. And in addition to doing that, we're going to be drawing the equipotential contours and then describing the hill that we would have that's associated with those electric potentials. Okay, so take maybe about 10 or 15 minutes to work on this one, and I'll walk around and answer questions as you guys have them. Okay, so let's go ahead and talk about this one. So what I give you to start out with is the electric field. I say this electric field E vector is going to be equal to some mag E times x hat, where this mag E is just some number. I could tell you like it's 10 newtons per coulomb or 5 newtons per coulomb, but this is just some number associated with how strong the electric field is between these plates. So this was the picture that I gave you. So this is the plus, this is a minus. And so I already gave you what the equations are that connect all of these things together. So this was the F vector is equal to Q E vector. This is Fx is equal to minus delta U over delta x. This is E vector, or Ex is going to be equal to minus delta V over delta x. So the first thing that we want to do is we want to take this electric field and go from the electric field to the force. And so conceptually what that's saying is I have this electric field here. What's going to be the force that acts on some charge if I put it in here? Okay? And the force that's acting on that charge is going to be related to what the electric field is and the charge that I put here. So we can say that if I want to go from here to here, I take this electric field that I have here, I plug it into this equation here, and that's going to give me that the force is going to be equal to Q times E times x hat. Okay? Everybody together so far? Okay. So now what we want to do is we want to go from the force to the potential energy. So again, conceptually, what does that mean? Well, if I have this charge in this electric field, I know it has some force on it. There's also some potential energy associated with it because it has the tendency to want to move. And so we know that if something has a tendency to want to move, that is going to, if I let it go, that's going to cause it to have some kinetic energy. So from this equation that I have here, Fx is equal to minus delta U over delta x, I can find what the potential energy is by kind of rearranging this so that delta U is going to be equal to Fx delta x with a negative sign. Okay? So we can take this and we can plug our fx in here, and so this says that u as a function of x, or delta u, we can leave it as delta u, is going to be equal to minus q mag e delta x. Okay. Now that we have the potential energy, we want to talk about what the electric potential is. So in order to find what the electric potential is, we know that U is equal to Q times V. We can move from here to here by dividing this delta U by Q. And so this says delta V is going to be equal to minus mag E times delta X. Okay? So that's all we were doing here. We start with the electric field and kind of go around to get over to here. Now we could check this one because we didn't actually use this equation, but is it true? So if I have my delta V and I want to get back to my my E vector, what do I have to do? Well, I take this, there's a negative sign there, it's a little hard to see. We take this, plug it in here, that's going to give me negative delta V, which is negative times a negative, mag E times x hat divided by x hat, and that's going to give me the component of the electric field in the x direction, which is just the magnitude of E. Was there a question? Or okay. So that's filling in the table, but we also want to draw our equipotential contours. So we know that the equipotential contours are going to be perpendicular to the electric field, so they're going to look like this. Okay. And then the last thing we want to do is to draw our hill. Well, drawing our hill is taking this and kind of tilting it, and we know that these values are going to be larger than these values here, and so our hill is going to look like that. If we put positive charge on the hill, it goes downhill. Positive charge goes downhill. Negative charge goes uphill. Okay? Any questions about this one before we move on? Yeah?
It says 6A, is there a 6B?
6A. I don't know why I label it like this. I made this last year. It's probably just 6, yeah. Or these were associated originally with some multiple choice questions. So 6A might have been just to fill it in. 6B might have had a question with it. I actually don't remember. Okay. So now what we're going to do is we're going to move on to the question that a lot of you wanted to answer to begin with, and that's, what does this look like for a point charge? So what I'm telling you now is we're starting with the electric potential for the negative charge, and we want to fill in the rest of the table. Okay? So go ahead and take a little time to do this. I think a lot of you guys know how to do this already because that's where you started with the last one. Okay, so let's go ahead and talk about this one because we do have other questions that we want to get through. But the whole reason why I was going through this exercise is these things are all connected to each other, and what you find when you're solving problems is it's easier to solve problems if you can separate the forest from the trees, right? So the tree might be an individual equation, but the forest is really the table that we're building with all of these equations. So let's show how we can go from one to another here. So for going from electric potential to potential energy, this is to say that we just multiply this by Q. And in principle, these don't have to be the same Q. And so what I'm going to do is I'm going to write it as this is U is going to be equal to minus K capital Q times Q divided by R, just to denote that these charges don't have to be the same. Okay. Now if we want to go to the force, this is going to be F F vector is going to be equal to K capital Q times lowercase q times r squared. This point's radially away, but we could also say that if this is along the x-axis, this could be like some fx, like we were doing before, and get rid of the unit vector. And the last one is going to be the electric field. So we can go from here to here, or from here to here by saying that the electric field in the x direction is going to be minus kq over r squared. Okay. Now, to plot this, or to draw our hill, well, let's first start by drawing our charge with our electric fields and electric potential contours. So we know negative charge has electric field lines that point towards it, and the equipotential contours are going to be perpendicular to those, and so those form circles, right? Because every point here is going to be perpendicular to the equipotential contours perpendicular to the electric field. Now, to draw our hill, drawing our hill is actually just plotting this function, right? So if we plot this function, we have essentially, this is negative 1 over r times a constant, right? What does the plot of 1 over r look like? Does anybody know what the plot of 1 over r looks like? Well, if it has really small values, so say it's something really close to 0. Well, what's 1 over 0? Well, mathematicians might not like me plugging in 0 there, but I'm going to do it anyway. What's 1 over 0? What's 1 divided by 0?
0.
Goes to infinity, right? Right? So you take a really small number, divide by 0, divide by like a half first. What's 1 over a half? 2. What's 1 over 4? What's 1 over 1/4? This is 2. This is 4. This is 1 over 8. This is 8. Separate these. So these are separate things. So the smaller the number I get in the denominator, the bigger the value is. And as I approach 0, this is going to go to infinity. Well, you have to take into account we have a negative sign here. So at 0, this goes to negative infinity. Well, what happens if I plug in really, really big values here? What's 1 over infinity? 0, right? So I start from negative infinity, I go to infinity, and so it's going to do something like that. Okay, so that's what our hill is going to look like. But let's see if this makes sense in the context of what we said for what's going to happen to positive, negative charges. Put a positive charge here. Put a positive charge here. How's this positive charge going to act on the hill? It goes downhill, same it always does, right? So positive charge goes downhill. Is that consistent with what we expect should happen if I put a positive charge here in the context of we have the physical charge here? Should it be attracted? Yeah, because it's a negative charge, positive charge. It should go that way. Okay? So, like I said, all of these things are connected, and sometimes in physics and mathematics, you can kind of get lost in the forest looking at a tree when you really want to look at the entire forest, and that's what I was trying to do with this exercise, is to kind of show you how all of these things are interrelated. Okay, so now that we've seen the forest, we're going to start looking at trees again. So we have a question here that involves a calculation. So we want to, LC is a clicker, essentially. So we know here that, or I say that an alpha particle, which is a helium nucleus, has a charge of plus 2e and a mass of 6 times 10 to 6.7 times 10 to the negative 27 kilograms. It passes through a region containing an electric field corresponding to a drop in potential of 500 volts. What is the change in its kinetic energy? So we're hearing things about energy, so when we're looking at the table that we built, we're going to want to use a particular one of these equations. Now, it's helpful here to draw a picture, right? Because we can draw pictures for the parallel plates now, and we think about like a drop in potential. So we have some starting point, we go to some ending point, and the potential is going to decrease. Okay. So go ahead and talk about this one, and then we'll solve it. Okay, so let's go ahead and talk about this one. So let's first start by writing down the things that we know here. And so we know that the charge, we're just going to call this Q, is going to be equal to 2 times E. I have E written here, so E is just the charge of an electron. We know that delta V, or the change in electric potential, is going to be equal to minus 500 volts, okay? So minus because it's a drop, it's a decrease. So we want to find what the change in potential energy, or sorry, the change in kinetic energy is, right? We want to find what this is. So somehow we need to connect that to the information that we have here already. And in order to do that, what we can first do is we can write down this relationship between the kinetic energy and the potential energy. So the kinetic energy is equal to the negative change in potential energy. And from here, what we can do is we can remember that the electric potential, V, is related to the potential energy by saying that U is equal to Q times V. So what that says is delta U is equal to Q times delta V. Okay? So take this equation, plug in Q times delta V here. So this is going to be minus Q delta V, which is going to be equal to minus 2 times 1.6 times 10 to the negative 19 coulombs times negative 500 volts. And what this ends up giving you in the end is a value of 1.6. This is going to be positive 1.6 times 10 to the 17? 16. Minus 16. Minus 16. Okay? And that's it. Okay. Everybody good with that one? Okay. But again, you can think about this. Think about the connections that we built. We had some electric potential we started out with, right? We had some change in electric potential. We had to go, and you imagine that the grid was still here. We had this part. We had to go to this part, so we had to jump over like this by using this U is equal to Q times V. Okay? It's positive. Okay. Okay, so we have another one here. This one says the electric field inside a parallel plate capacitor is 4.5 times 10 to the 3 newtons per coulomb. If the excuse me. If the distance between the plates is 2 centimeters and a negative plate is at a potential of minus 45 volts, what is the potential of the positive plate? Draw a picture and make sure that the electric potential on each plate matches the direction you drew the electric field. Okay, so again, think about this in terms of the connections we drew. We know that we want to find what I think we want to find some electric potential, right? We want to find what the value of the electric potential is on the positive plate. We have some electric field. So think about how we go from electric field to electric potential, okay? Okay, so let's talk about this one. So for this problem, the last one we were talking about how we can relate the electric potential to the electric potential energy. Now what we're doing is we're talking about how we can relate the electric field to a change in electric potential. So to start with, what we can do is we can draw a picture here to represent what it is that we're trying to find. So here's our positive plate. Here's our negative plate. So this is what I'm going to call V negative, okay? V negative is given. This is just going to be the minus 45 volts, okay? V positive is what we're trying to find. We also know that the electric field is going to point from the positive to the negative, and that this is separated by some distance of, this distance is going to be equal to 0.02 meters, okay? So now we have everything labeled. The next thing that we want to do is to write down the pertinent equation. And we remember that there's one other thing that I'm missing here. This is the electric field. E is going to be equal to 4.5 times 10 to the 3 newtons per coulomb. Okay, so we have everything labeled now. And what we're trying to do is we're trying to go from the electric field to the change in electric potential. And that equation says that Ex is going to be equal to negative delta V over delta X. Okay, but we can expand this delta V here to say that this is minus V minus plus, minus V plus. Okay, right. And the reason why I'm writing it like this, and we can think about it this way instead of V plus V minus. This is VF. This is VI, because the electric field originates, or it starts from the positive plate and it goes to the negative plate. So that's why this is going to be V minus minus V plus, and this is divided by delta X. So we can rearrange this by multiplying both sides by delta X, and so we have Ex delta X is going to be equal to negative V minus minus V plus. Okay, we can distribute this negative sign in here. That's just going to make this look like this, and then move this to the other side. And so what we have is, this is Ex delta X plus V minus is equal to V plus. And so when we do this calculation, what we end up finding is that V plus is going to be equal to 45 volts. Okay? All right. So as you're going through this, just make sure that you're drawing your pictures, and then the pictures are matching what our equations are saying. And if you're matching these things, it's going to be a lot easier for you to solve in the end. Okay. Any questions about this one? Okay. So moving on. So here I have some positive charge on the left side and a negative charge on the right side, where we say that both of these charges have the same magnitude. So the magnitude of each charge is 2 nanocoulombs, and they're separated by 15 centimeters. We want to find what the electric field is between the charges at the midpoint, the electric potential at the midpoint between the charges, and the force that would act on the 3 nanocoulomb, the force that would act on a 3 nanocoulomb charge if it was placed at the midpoint. Okay? So go ahead and talk about this one. Okay, so let's talk about this one. So for the first problem here, what we want to do is we want to find what the electric field is here. So in order to find the electric field, the total electric field, E total, we want to say that this is going to be the sum of these two electric fields. So this is electric field 1, or the positive electric field, and the electric field from the negative charge. We can see that the electric field from the positive charge is going to go this way. The electric field from the negative charge goes the same way. And because these have the same charge, and we're looking exactly halfway in between them, we can say that the magnitude of these electric fields is going to be equal to the same thing. Okay? So now what we can do is we can explicitly calculate what one of these is and then just double it. And so what we can do is we can say E plus is going to be equal to KQ divided by R squared, where this is going to be equal to 9 times 10 to the 9 newtons per coulomb squared times this charge, which is 2 times 10 to the negative 9 coulombs, divided by the distance to where I am finding the electric field squared. And so that would be 7.5 centimeters, but because we need to do this in meters, this is going to be 0.075 meters squared. And so when we do this, we end up getting 3,200 newtons per coulomb. Or when we double this, we end up finding that 2 times this, so E total is going to be equal to 6,400 newtons per coulomb, okay? Now, in order to find the electric potential at this point, what we can do is we can calculate, again, explicitly what each one of them is independently, and so this is going to be V total is going to be equal to the sum of these. So this is V plus V minus. And so what we can see here is that we have the same distance, same charge, but this one's going to be negative. And so this is going to be KQ divided by R minus KQ divided by R. And so this one is going to be equal to 0. Okay? Now, in order to do the last one, you could explicitly do the calculation again. You could say that the total force is equal to the sum of the forces acting on the charge, or what you can remember is if I have my electric field and I want to find what the force on a charge is in that electric field, I just say that F is going to be equal to Q times E, and when we plug that in, we end up seeing that this has a value of 9.6 times 10 to the minus 6 newtons. Okay? And that's it. Any questions about this one? Yeah?
Why did you subtract?
Because it's a negative charge. Because what I kind of artificially did was I said, well, this is a charge Q, this is a charge Q, but it's a negative charge. So that's why ultimately I subtracted here. Okay?
Is that 0 or is that?
Which one?
The equation we just talked about.
This one? Yeah, this is a 0. This is a 0. Yep. Yep.
For the same one you got would it be double 9.6?
It shouldn't be because I already doubled it here. So I found what the total force was by taking the electric field and just multiplying it by the charge. Unless I might have made a mistake on my calculation. But in practice, what it was that I did was I calculated what the electric field is, and that's the total electric field. And I say, well, I'm going to just plop a charge in here and say, I'm going to put a charge of 3 nanocoulombs here. But if I know what the electric field is already, I actually don't care about what these charges are doing anymore. I just take the electric field that they create, which I calculated already, and I multiply it by the charge that I'm putting there, because we know that F vector is equal to QE vector. Okay? But if you wanted to do it the other way, what you could do is you can say, go back to doing this like this. We could say that F total is equal to the force that the positive charge acts on it plus the force that the negative charge acts on it. But the force that the positive charge acts on it is the same as the force that the negative charge acts on it because of the same distance and same charge, right? So this one's going to, if I put a positive charge here, it's going to repel it. Again, if I put the positive charge here, this negative charge is going to attract it. But because it's the same distance, same magnitude of the charge, these two forces are the same. So if you want to do it like that, then I could calculate what the force is just that this one acts on this one, and then double it. Okay?
Yeah.
All right. Other questions?
When we did that collectively, we got your answer, which is like from the E field, and then we had to multiply it by 2.
Yeah.
Yeah, so when we do all of that like force total stuff, we like with Coulomb's law or whatever, we got 9.6 times 10.
Oh, so you got this up here?
Yeah, up there, and then we multiplied it by 2.
I guess my key might be wrong. My key might be wrong then, because I don't. Oh, I can do this quickly. So this is 3 times. No, the numbers work out right here when I multiply this by 3. So 6 times 3 is 18. No, that doesn't work out. That doesn't work out. Hold on. So this is 6.4 times 10 to the 3 times 3 times 10 to the negative 9. And so this gives me a negative 6. This gives me an 19.2 times 10 to the negative 6. So this is what you should have. This is what you should have. Yeah. So my key was wrong. Blame the key. I didn't do the calculation myself. I'm sorry. Okay. But I know the way. This is the way that you're supposed to do it. Okay. All right. So now we've been talking about the electric potential. In the last couple of minutes, we want to talk about how we're going to use that in circuit analysis. And so when we talk about electric potential, that's equivalent to talking about voltage in circuits. And so a battery like the one that's shown here schematically maintains one terminal at a higher potential than the other. And so here I say I have some negative potential on the left, some positive potential on the right. And what we do is we connect this with wires. So what we'd like to do is we'd like to think about why electrons are going to flow in the conducting wire that I've drawn here in terms of what we've talked about from the electric potential. Okay, so go ahead and talk about that. So think. Okay, so let's go ahead and talk about this one real quick, and then that'll be it for today. So we have this battery and some wire associated with it. So what we're going to say is we have this setup here. So this is minus, this is plus, and then we have a battery or a wire that connects these. And what we'd like to do is we'd like to say, well, what's going to happen if I put some negative charge here? How's it going to behave? So what do you guys think? What's going to happen to this negative charge? Is it just going to sit there? No, it shouldn't just sit there. So it's going to go around like this, right? Now, there's kind of two ways to think about this, or three really. So if this is the negative side of the battery, you could kind of think about this like there's negative charge here, and so that's going to repel things from this. The positive charge here, it's going to attract it like that. So that's thinking about it in terms of charge. But we've learned that we can think about things in terms of charge, we can think about things in terms of electric field, and we can think about things in terms of electric potential. So what's the electric field going to look like here? Well, the electric field is going to leave the positive and go to the negative. Okay? Now, if I have an electron, is it going to go with the field or against the field? It goes against the field. So it's going to want to go that way. So that's thinking about it in terms of the electric field. But we can also think about this in terms of the electric potential. So if we had some hill like this, and we put an electron up it, is it going to want to go down the hill or up the hill? Up the hill, right? So up the hill is the positive side. Down the hill is the negative side, okay? So those are our three ways that we can look at what this electron is going to do in the circuit, okay? So that's it for today. I'll post the homework hopefully today, if not today, then tomorrow, and it'll be due next class, okay? Yeah, what's up?